for the nice introduction. Okay, recording in progress. Perfect. So, thanks again, Andrea. And yeah, today I'm going to talk about some results that I obtained during my PhD and the challenges and tools for consistent seismic catalog analysis. This is, of course, a joint effort among my research group at ATH, and I'm glad to share them with you today. So let's start by saying why seismic catalogs and why those are important. Seismic catalogs usually come with different formats. You may know if you're dealing with this, but most important, all of them carries information about the hypocenter, the spatial location of these earthquakes and all the metadata associated to them. These datasets are super important for the correct understanding of fault systems and seismotectonic studies, as well as for local earthquake tomography, for instance. And last but not least, also to produce highly good seismic hazard map. At the moment, we have tons of data. We have more than 800 terabytes of data across ADA nodes that can be easily downloadable. They are at hands of everybody, and that can be processed more or less easily by the community. Of course, this amount of data is increasing manifold, also with the distributed acoustic sensing that is coming, is the new methods that are rising. So how can we handle all of this data? So one may think that more data, of course, bring more models. We increase the coverage of remote region, we improve the seismic hazard model, and also we increase the potential resolution for seismic tomography studies. Unfortunately, most of these data sets comes from heavy workloads in human-driven seismic observatories routines. And these maybe can lead to some inaccuracy in measurement due to the long duty session of the operator, and eventually to some inconsistencies in the downstream product. So the challenges, if we want to pursue this procedure in an automatic way, is to be able to correctly do the seismic phase peaking and the event and the association of these phases in order to update the seismic velocity models, and also to do the automatic peaking refinements and the manual filtering of this observation, providing the final event relocation and the magnitude calculation. So what I'm trying to do in this talk and try to show you is if I could create a semi-automatic procedure that can handle a routine big data analysis for seismic observatories, and also if we can obtain high quality research products from it. So with no further ado, I'm just introducing, this is the outline of the argument about the AlpArray research seismicity catalog creation. I will introduce you to the area, then I will show you the methods that I applied and that we developed, the results we obtained, and therefore the conclusions and the outlook. So the Mediterranean area is a complex involved by complex geodynamical processes among the European, the Adriatic, and the Mediterranean microplates. This geologically complex region, of course, made this area with a moderate to slightly high seismic hazard, and especially for the density, because of the densely populated areas at the center of this area, is also even more important to correctly determine the occurrence of events. At the moment, the greater Alpine region that you see here with the white contour line is monitored by two international agencies, the EMC and the IEC, plus 11 national seismic observatories, all of them with different competence region, as you can see from the figure. So while these periodic bulletins provided by the national observatories are perfect for local and national studies, sometimes it can be cumbersome to effectively merge them for regional or international studies. In fact, the seismicity catalog merging is somehow a painful procedure because of the different event location algorithms, magnitude scales, and velocity models adopted by the individual observatories. In fact, doublets report or may occur, and especially it's really difficult to pair low magnitude events because, of course, of the problematics that I said before. One project that probably you have heard of is the AlpArray project that took place between 2016 and 2019, provided an unprecedented possibility to uniformly investigate the greater Alpine region by deploying a temporary broadband station that aimed at the better understanding of the Alps, the Northern Dinarides, and the Northern Apennines intraplate relation. Of course, all the data collected will be able, with all this data collected, we will be able to do a seismic tomography, a seismotectonic studies, and also earthquake statistics. All of these studies, though, needs to start from a consistent and precise seismicity catalog. And again, I cannot stress enough that the AlpArray project was able to fill the gaps among the permanent network station. Almost 300 temporary broadband stations were deployed along with ferry OBS in order to obtain with this hexagonal packaging almost a 52-kilometer interstation distance. Of course, these automatic problematics are mainly represented by dealing with complex crustal seismic phases that derives from this huge area of investigation, plus their correct identification, and therefore also, and thus the correct event association of them. For this, we created a semi-automatic multi-step procedure that involves 3 different software: SeisComp3, the AlpPicking library, and the Velesta software, in particular, the joint hypocentric determination approach that it offers. This is the multi-step, simplified procedure of our method. It starts with SeisComp3 program in order to provide a preliminary automatic catalog. As you may see, the amount of continuous data stream provided more, almost 40,000 events. Unfortunately, though, all of these events are outside our interest, our area of interest. Plus, some of them are erroneously or associated or fake, so-called fake events. Here is an example of these of 4 fake events that, as you may appreciate, are actually erroneously located. For instance, this in panel A, of course, belong to the Aquila sequences, but it is anyway relocated off the border of Corsica, and so on and so forth. Also, may occur that 2 different events are actually occurred at the same time, are recorded to a different subset of the network, but are merged actually by the associator erroneously in the middle. So this event filtering procedure was necessary in order to have a clean data set automatic, a first preliminary automatic catalog. And in fact, we reduced the number of events up to almost 3,400 events by spatially, as you see from the contour line that we carried out most of the other events, and based on magnitude, and also based on the data availability that was obtained at that time period. Then the core of our procedure of refinement of these peaks of this location is given by the adapt JHD Velesta procedure, done in 2 different rounds, because as you will see, the adapt picking system needed a an initial prediction of the first arrival peak. And in order to improve this precision, we needed to also calculate the minimum 1D Pwave velocity model and the associated station delays in order to improve this prediction. A final single event mode run with less software, we got rid of the lasting outlier observation, plus providing the final absolute location. So what is ADAPT? ADAPT, as I said, is a picking toolbox that comes with the idea that if you are an experienced, for instance, an experienced seismologist, and you are provided with this waveform, and we ask you, where is the first arrival of this earthquake? Well, you may as well zoom in to the most probable arrival time window of your phase, and then proceed with an unpicking and then an uncertainty assessment of your observation. One observer may peak here when actually the low frequency starts to enter, here when actually we start to see a change in amplitude, and maybe one other can actually peak where the amplitude is completely above the signal to noise ratio threshold. Well, the fact is none of them is incorrect somehow. The point is, and the difficulties, is for them to be consistent throughout their picking session in order to be able to provide a consistent uncertainty assessment. The point of this is that this point is actually well done by automatic picking algorithms that in fact, they behave the same way if provided with the same waveform. And in order all of these, and this is important, especially when dealing with so much data. And actually there is no escape by using automatic picking algorithm. So the ADAPT acronym stands for Adaptive Picking Toolbox, because the aim of this toolbox is to be scalable and customizable for the user needs in different regional study region. It's an object-oriented picking library, and it comes fully embedded with, and is fully compatible, with the other major scientific library in the Python environment. Again, the idea of using a multi-picking approach, that is in fact the whole point of dealing with ADAPT system, is that each one of them is actually behaving as an independent observer, meaning that each one of them is sensitive to different change in the time series properties. At the moment, the system is supporting 5 different algorithms. The first one, the byte picking algorithm, is just used in refining the initial predicted first arrival, and eventually providing not only the first arrival, but also secondary phases arrival, because it's an iterative picker. The other 4 instead, quote standard picking system, are actually used to do this ensemble verification. From this synthetic, you see that there are different sensitivity, as I said, and the different property, physical changes in the property of the time series. And at the end, because they pick slightly, in this case, just 2 different samples, with this uncertainty band, we can better define the onset nature and better define actually the real uncertainty of our observation. The ADAPT picking system, actually the tuning was done by analyzing 11 events handpicked by one experienced seismologist, and each single picker was trying to minimize in their own way the residual among the manual and their automatic system. We did this by using a grid search tuning approach, and we selected, of course, the set of parameters that better minimize our model. And with this in mind, this is a kind of standard workflow of the ADAPT system that starts, of course, from the retrieval of the waveform, the prediction of the time, as I said, but the real core system of this system is this multipicking approach, where we provide two different time windows in order to emulate like an experienced seismologist would do: zoom in, zoom out, move the time window. And we are able to provide the different time windows to each individual picker in order to accommodate their individual properties, inner properties, and way of seeing actually these changes. So these two different time windows combined in this example show us the difficulties that one would have in discern correct or erroneous phase identification if using an individual picker. In fact, in this picking slice 1, we see that most of the pickers are coherent to look at the first arrival, while the single AC picker was actually falling in detecting the second arrival. This is not occurring if we see the picking slice 2 that was actually zoomed in, where the entire set of observer of pickers were actually picking to the same phase. Please note that this is a complex situation at the station due to the triplication zone that at this distance may actually mix up the reflected phases from all plus the first arrival, PM and PGs. So it's a kind of the messy spot actually, where it's for automatic system is difficult to perform. Plus, I didn't mention before that the display here of the time windows is the same just for the sake of clarity. As I said, each individual picker is provided with different time window. Then what do we do with this pool of observation? We then pass through the peak validation layer of our system, where actually we are able to discern among valid and faulty observation through a statistical jackknife approach. Another thing that our system with this approach, let's say, one is able to do is to define the uncertainty band not in a Gaussian way, like most of the systems does, but also providing the earliest and latest arrival as the real uncertainty of observation. The final absolute peak, of course, is given by the median of this valid observation pool. Here is just an example of what is actually meaning, and also to stress even more the reasoning why we are using a multiple picking algorithm. These are the results of the residual on the left. You see this confusion matrix. These are the residual of the multi-picking stage layer, where we have the automatic individual picker compared with the manual observation. On the x-axis, you see the classes that were given to the manual observer, that the manual observer gave to the observation. We go through class 0 being the highest and 4 being the lowest. And on the y-axis, the individual automatic picking algorithm. So what happened is that the combination, as I said, of this multi-picking stage plus the validation layer led us to the final residual among the final adapt picking system and the manual observer. As you see, actually, with this automatic system, we are able to reduce a lot the uncertainty given by an individual picking algorithm. And yes, although we decrease somehow a lot with the total number of final observation, but we have an extreme quality obtained with automatic system. After adapt, the picking of adapt, it entering the game the joint hypocenter determination of the last. That is actually used mainly as a filtering tools, both at an observation and also at an event level, full event level. One should say that there is a classification that comes along with this the last joint hypocenter determination approach. We decided to declare an event well locatable if it's actually showing more than 7 observations and an azimuthal gap less than 180. A poorly locatable instead comes with the most important and, how can I say, dividing factor is the gap major or equal than 180 degrees. To explain better what is actually doing the joint hypocenter determination in 2 different rounds is actually exploiting the ensemble of our observation in order to increase the quality of our final location and solution. Here on the panel A, you see 2 different sub-panels to divide the lower magnitudes event and higher magnitudes event. In this figure, on the x-axis, you see the delta among the location azimuth gap of the second round of of picking and filtering, minus the gap of the first round. On the y-axis, instead, you see the number of observation obtained, the delta of observation obtained after the second round and after the first round of our procedure. This panel, what does say to us that in the second round, we are able to increase the number of observations while also reducing the azimuthal gap of this location. And while this is much more evident for smaller events like one would expect, is also pretty much stable with the higher magnitudes events, as still they are already well detectable and constrained in already at the first round. I mean, in the different color, you also see the increase of quality in the blue circle of an event coming from a poorly locatable classification in the first round, increased to the well locatable classification in the second round. And this because here in panel B, you see a synthetic example of this, of why this is happening, is because maybe an event was outside the network that recorded it, and in the first round, and in the second round, instead, by increasing and by well constraining the location after the first round, we are able to reduce the azimuthal gap and increase the number of observations at those stations. Although the usage of joint hypocenter determination is really useful to get rid of this outlier and to improve our location, still there may be events that show a weird or probably erroneous depth for the region of interest. And this is because the joint hypocenter determination gets rid of the really clear outliers that pop up from the ensemble of our observation. But still some outlier, especially in arrival time, may still remain in the pool of peaks associated to the event. For this reason, we decided to add this additional step, as I said, in the single event mode still provided by the VLS software, where actually we iteratively locate our events in order to remove every individual observation that show a studentized residual less than higher than 0.5 seconds. The results, of course, is that most of the deepest event were actually pushed up and correctly located in their own in the most probable spot. This is a real case of what I was just saying. An event that was actually recorded here with the highest azimuthal gap after the second round of joint epicenter determination, and that after the filtering of these erroneous observation in red traces here, we are able to put again back inside the network with this blue star, the same event, inside our network. So this final cleaning is still very important in order to produce better location at the end. In fact, if we compare the residual of these events of the same events produced by SE3 in the initial catalog, we see a huge and marked reduction of these residuals. This means, of course, that our procedure was able to filter out the outliers and consistently locate, improve the location of our event. As a result, we obtained the AlpArray research seismicity catalog, and this is composed by almost 3,300 events. Most of them are actually well-locatable events, and show local magnitudes that span 0.4 to almost 5. And the precision of these the location, of these well-locatable events was done through a shift test, where we actually perturbate our final location, making sure that we perturbate them constantly along the free direction, and relocating them in order to see the error that may occur. That is, in this case, for such a big region, really outstanding. In fact, the error is 0.7 kilometer in the epicentral distance, and 2 kilometers instead in depth. The seismicity that our catalog show is actually fitting the general seismotectonic trend of the microplates that actually are in game in this region. We see, for instance, that the cross-section that goes through Corsica up to the Eastern Alps is actually showing nicely the subduction of the Adria Mole towards the Tyrrhenian Mole, as well as the section across the Western Alp foreland to instead Piemonte, where we can appreciate the well-reported in literature shallow seismicity in the Western Alp foreland. And also we can appreciate the seismicity derived from the uprising mantle material that is called the Ivrea body, just beneath, eastward of the Western Alp. Another thing that one should take into account when dealing with these kind of catalogs is actually to compare them with the same kind of catalog, therefore regional catalog. In this case, we did this by comparing our catalog with the EMC regional catalog for the same time period, and for the only the magnitude 3+ events reported. On the left here, I'm showing the in orange circle the seismicity reported by EMC in the 4 years of the AlpArray project of magnitude 3+. In black crosses instead, you see the reports of the EMC for the longer period seismicity that goes through, that goes through 1998 to 2015. And we can see that the major tectonic lineaments are more or less active throughout this 20 years period. And so what we did was actually to compare also the 4-year seismicity of our catalog, magnitude 3+, with the magnitude 3+ still in orange circle of EPOS. And we see that there is a nice correlation of these two. Although one may think, different for two different smaller regions, being these tectonic lineaments and also this one in the Mur-Munsal fault, where actually magnitude 3 events were reported by the EPOS and were lacking actually from our side. But this is actually not true. In fact, we were able to pair this event just with a different magnitudes report. In fact, you see here the smaller circle, empty circle, black circle, are actually the event reported in our catalog with a magnitude less than 3. And this means exactly this. This can be results of actually providing different magnitude scale together, like is actually doing the EMC. So for this reason, we were actually able to pair this event just with the different magnitudes. And this actually brings us to another key point and another key major achievement of this study. The point that we should be able to create, we did actually create a uniform magnitude, local magnitude calculation for the entire region. Here, I'm just showing you what actually is happening if we pair 6 different national catalog of the different national observatories with our final catalog. And we see that we can reach different, let's call it pairing magnitudes completeness, depending of course on which scale is used by the individual observatories. This is maybe more one may appreciate this even more by seeing the 4 panels here, where we are actually comparing our unified local magnitudes against the local magnitudes of the individual observatories. This is not to say that there is a better or a worse magnitude scale. It's just to say that it's difficult to pair just by magnitudes, that a lot of events may show, like for instance, in this OGS scaling, we clearly see that in our magnitudes scale, we underestimate the magnitudes at lower magnitudes report of OGS, while we tend maybe to, or there is a trend of overestimating higher magnitudes events compared to the one in OGS. So this is actually pretty important. I cannot stress enough that having a unified magnitude calculation across the entire area make us able to compare the seismicity at the different spots in the Greater Alpine region. So this is, of course, led us to the bread and butter statistical analysis of a catalog. That is, in fact, the magnitude frequency distribution analysis. In order to define the statistical our magnitudes of completeness, we used three different catalog-based approach, being it the Lilliput test, the B-value stability, and the median-based analysis of the segment slope. All of these methods are widely used from our community to declare the completeness of the catalogs. Although we use the three different methods together in order to get a vibe and to get a more consistent analysis of the final completeness that we actually at the end state to be equal to 2.4 and with a b-value of 1.05. This is the completeness given by the by the b-value stability algorithm. Last but not least, there is also the minimum 1D model, Pwave velocity model of the GAR. And this is an update of previous studies that was done by Diel et al. In 2009 for a smaller portion, mainly focused on the central and western Alps. And we see that there is, although the layering, is a bit different, there is a consistency of this 1D profile together with the previous study. There is anyway not a clear jump of the classical MO velocities because we still need to think this as the averaging of all the velocities contained in a single layer. And for such a great area, this of course may see some correction due or not so clear MO jumps due, of course, of the complexity that the MO profile has in the area. Also, the station delays correctly identify the site effect that may derive, for instance, from the slowing, for the slower velocity in the pop lane, or from the higher velocity provided by the faster travel path that events in Italy are doing towards upwarding towards the MO. So also these results are important in this sense that providing a unified velocity model for such a big area may allow us to also link to the same consistency, to the same error quantification of our catalog of the long-term seismicity of the 20-year maybe, or as long as one could go back with the recordings. So in the end, did I create a semi-automatic procedure? Yes, I did, although still can be, of course, improved and can be applied to different region in the region of interest, and maybe also, I don't know, in other subduction zones. The adapted JHD VLS, though, is scalable, and for this reason will be interesting also to be applied in smaller scale, at a smaller scale. And then we obtain a higher quality research product in the sense that the AlpArray research seismicity catalog is actually providing us an unprecedented starting point for several studies. In particular, again, just to remember, it's almost 3,300 events with a higher precision, and also is able to highlight the major tectonic lineaments, being it consistent with other national and regional observatory report. This unified local magnitudes calculation, of course, with a completeness of 2.4 is much useful for the comparison of the seismicity across the different regions in the area. And also we were able to reach a consistent pairing of magnitudes 3+ events reported by the national observatories. Again, at the end, the minimum 1D model and the station delays are maybe also the most important tools to link the past and the future eventual seismicity with the same consistency of our catalog, providing then a useful data set to improve the seismic hazard mapping in the area. So with this, of course, is one of the outlook of our studies. And also another possible study could be to convert our local scale magnitudes with the moment magnitudes scaling, maybe using updated attenuation function for the subregion eventually. And also, of course, the dataset can be used and is currently under investigation for a regional local earthquake tomography that may help even further the understanding of the GAR seismotectonics. So thanks for your attention, and I'm open to questions.